Welcome to PdMA Corporation, home of the MCEMax. I'd like to thank you for joining us as we continue along in our case study presentation series. My name is Todd Gunderson, the Vice President of Sales and Marketing, and today we have with us, once again, Noah Bethel, the Vice President of Product Development.
Hello from sunny Tampa, Florida.
Well, Noah, once again, we have an excellent case study given to us by our good friends down in South Africa, a service company, and the title really explains it, Deep Below the Earth's Surface in a South African Platinum Mine.
Man, that sounds like a National Geographic moment.
Absolutely, it does. The MCEMax prevents catastrophic failure. So without further ado, let's get into the actual information and work through this case study. Well, here's the problem, right? The motor is used to lower the water table in a platinum mine. So without this motor, you can't get deep down, can't get the mineral out of the ground. I think platinum is selling for $1,745 per ounce. So obviously we want to be able to pull this precious metal out of the earth, right?
Fairly critical motor.
Pretty critical, right? So we're experiencing some spurious trips. And another thing, 3 weeks to take this motor into and out of the actual location.
Wow, that really elevates the decision-making skills, and that you do not want to make a mistake deciding to change this motor out because you're dealing with major potential downtime. And the spurious trips are difficult. It happens. There's no drive related to this motor from what I'm hearing and what I see. So without a drive, the spurious trip really raises the flag as to some type of potential motor anomaly or even a mechanical issue.
So we're going to look at some data and see how the MCEMax can help us out. So it's basically straightforward here, 50 hertz application. That's what they use in South Africa. 82 full load amps, 1,000 horsepower, 785 kW, 4-pole motor, AC. Pretty run of the mill.
Yeah, I mean, there's not only 3 weeks downtime, but this is a fairly decent sized motor, and one that's going to be costly in itself. Any repair to this motor is going to be, many tens of thousands of dollars, even up into the hundreds of thousands of dollar range, depending on the failure mode.
So our service company, they took essentially an inrush startup of the motor, and we can use it 2 different ways, right? We can either get the inrush of it, the most stressful time of the motor, or we can do like he did here and use it as a form of a process analysis. What does this tell you?
This is a great test. In fact, it's an RMS envelope of the current being fed to the motor. In this situation, it looks like about 80 amps modulating plus or minus 3 to 5 amps. Now, that modulation, that rise and fall repeatedly of the current signal or the amplitude, could be a mechanical. It could be simply a mechanical feature. It could be a part of the application, a load change that is normal, or it may not be normal. That's where it becomes kind of critical to have either a baseline comparison or a like motor in a similar application.
Well, it just so happens that there is a spare motor, so we'll take some look at that data.
Wow, what a difference. I mean, that is a much more stable signal. You can see it looks like the amperage is right around 70. So for the similar or same application, we have almost 10 amps less. Very little modulation in comparison, which really starts to point towards a possible rotating impedance variation. Now, that sounds real technical, but it basically starts to allow us to focus a little bit on the rotor as a possible influence to this changing current.
So that's one indication that we may have some rotor anomalies, but also look at the power itself being used by this asset. The screen before we saw was up in the 80s. Now for the same application, we're in the 70s. Are we saving money?
No question. Apples to apples, application to application. If you can save 10 amps on a regular basis, that does add up over the year.
Now we're going to look at it from another piece of technology in the EMAX, and this is our current signature analysis. And red is bad, right?
Red is bad. That's an ugly spectrum there. No question, when the pole pass frequency sideband is reaching elevations of that height, an immediate flag has to go up. Now, that doesn't dismiss the need for correlation. Our tech support department often recommends 2, if not 3, separate indications of rotor anomalies before we make an action or make a call on this. And when you're talking 3 weeks to pull and replace this motor, this is not a small decision to be made.
No, so what do we also want to do? We want to look at that spare again. What is that showing us? Well, as you see here, a little different, right?
Very different. A couple things that stand out to me on this. Number one, obviously, is the amplitude difference. With similar noise levels and identical loads, we're dealing with a significant drop in pole pass frequency amplitude. The other thing to notice is that it's closer to the line frequency, which means the slip is less. One other thing to remember is with elevated impedance values, it causes a lower current drawn from the motor for the same load. The slip increases and the speed goes down. This is all being indicated with those comparisons.
Now, those previous two tests were online data. What about offline? What is this test telling us?
This is a great and third piece of information to make this very difficult decision.
3 strikes and you're out, right?
I like that call, yes. And if I was involved in this, knowing the cost that we're dealing with and the risk that we're making to yank this motor up from so deep, and it's the right decision to make. And in this situation, a very smooth sinusoidal, waveform should be seen on a healthy rotor. In this situation, it's not. We have a significant and repeatable drop off in inductance on the backside of these sine waves, and it repeats from phase to phase, all this pointing to a likely rotor defect.
Well, let's pull it out and let's see what we get. Wow. 9 out of 58 rotor bars damaged.
Goodness, yeah, this is a couple things stand out. I mean, that's a large number. I think we were looking at 17-18% of the rotors that are potentially being removed from the circuit. That means the opposing impedance under the stator windings goes way up. The other thing I'm noticing, and it's real obvious in this picture, is the open bar design. The slots are open, which really elevates the risk of a possible bar wanting to come out of the slot. This is a high risk to stator damage.
It's interesting that you say that, right? Because here's our next picture, and lo and behold, just what you had said possibly could happen, looks like it's starting to happen.
Wow, yeah, this was in terms of a major preventive of a catastrophic failure. This is just like the arrow says there, millimeters. I'm thinking that this bar is probably millimeters away from the stator windings and potentially taking a rotor repair and turning it into a rotor and stator repair, easily doubling the actual repair costs.
And so by catching the problem early, like you said, we were able to save, or the mine was actually able to save a couple 100,000 Rand. On top of the fact that you didn't lose a lot of production and you were able to keep the water levels low so that you could mine that ounce of platinum coming out of the ground at $1,745 an ounce. You don't want to lose production in that, do you?
Oh, and the numbers just keep adding up, and what a great catch. And hats off to the reliability team there.
Well, as always, we'd like to thank you for your time. And if you have any questions, please contact us at www.pdma.com or give us a call at 813-621-6463. Once again, we'd like to thank you and thank Noah.
My pleasure.
And you guys have a great day.